All right, let's talk about one of the coolest, most intuitive tools in all of machine learning, the decision tree. We're going to break down how machines actually learn to make choices, and you'll see it's probably way simpler than you think. I mean, you have to wonder, right? We see it all the time. A bank approves a loan, a doctor's app suggests a diagnosis, and you might be picturing some kind of super complex sci-fi black box doing all the work.
But what if I told you the whole idea is based on something you do literally every single day? It's just a simple, branching set of questions and answers. And that right there is the big idea behind a decision tree.
Okay, let's dive into it. When you get right down to it, a decision tree is really just a flowchart. Seriously, think of it like an upside-down tree that just maps out a series of choices to get to a final answer.
So picture this. We're trying to build a little model to decide if we should play outside. The very first question the tree might ask is a simple one. What's the weather like? Is it sunny, cloudy, or rainy? See? Each one of those answers sends us down a totally different path.
So this simple flowchart has a few key parts, and in the world of machine learning, they've all got these official-sounding names. Let's break down the anatomy of how this decision gets made.
Everything kicks off at the top with what's called the root node. This is our big initial question, like what's the weather? It represents our entire pile of data before we've started sorting anything out. Now the answers to that first question, sunny or rainy, they create the branches. And these branches can lead to other decision nodes, which are, you guessed it, just more questions. Like, okay, it's sunny, but is the humidity high? Or, it's rainy, but is it windy?
And then finally, every path has to end somewhere, right? That's the leaf node. It's the final call, the actual prediction. This is where the tree stops asking questions and just says, go play or stay inside. Game over. Okay, so we know all the parts of the tree, but how does the computer actually build it? How does it figure out which questions to ask, and just as important, in what order? It really is an art. The art of asking the right questions. Well, the way it works is actually pretty clever and, surprisingly straightforward. The algorithm looks at all the data, and it asks itself, what is the one single question I can ask that will split this data into the cleanest, most organized groups? Then it just does that again, for each new group, over and over, until it can't make the groups any cleaner. Okay, but that leads to the million-dollar question, right? How does it know what the best question is? How does it figure out that asking about the weather is way more helpful than asking what day of the week it is?
It all comes down to this one idea, purity. The whole goal of the algorithm is to make each split in a way that the new groups are as pure as possible. And what's a pure group? It's a group where pretty much everything has the same outcome. So a perfectly pure group would be one where, say, 100% of the time the answer is go play.
And this right here nails the idea perfectly. A good split is one that reduces the chaos. It takes a messy, mixed-up group and creates new groups that are way more uniform. A bad split, well, it doesn't help much. The new groups are just as jumbled as the one you started with. The algorithm is always on the hunt for those really good splits. Now, to do this, the algorithm uses some math to score every possible question it could ask. You might hear these fancy terms thrown around like Gini impurity or information gain. Don't worry about the names. Just know they're tools the algorithm uses to measure which question will create the most purity and bring the most order to the data.
Okay, so like any tool, a decision tree isn't perfect. They are incredibly useful, for sure, but they also have some weaknesses you have to watch out for. So let's take a quick look at the pros and cons.
So you can see a bunch of pros and cons here, but let's focus on the big ones. The absolute best thing? They are so easy to understand. You can literally draw it out and show it to someone. But the biggest weakness is that they have a bad habit of overfitting the data. The key thing to remember, though, is that this simplicity is also its greatest strength. It makes decision trees the building blocks for some of the most powerful algorithms out there, like random forests.
And this quote just perfectly sums up that whole overfitting problem. The model basically memorizes the answers to the test questions instead of learning the actual subject. So it does great on the test it studied for, but when you give it a new problem it's never seen before, it completely falls apart.
All right, so we know how they work. We know their strengths and weaknesses, but where do you actually see these things in the real world? How does this simple flowchart idea turn into something powerful?
Well, for starters, in healthcare, they're a huge deal.
They can help doctors diagnose a disease by following a flowchart of symptoms. They can help predict how a patient might respond to a certain treatment. And they can even sift through data to find the biggest risk factors for things like heart disease.
And of course, the world of finance totally relies on them. When you apply for a loan, there's a good chance a decision tree is helping to assess the risk. And they are absolutely critical for banks in spotting fraudulent transactions in real time.
And then there's marketing, where they're basically used to understand, well, you. They help companies group customers together for smarter advertising. They can predict who's likely to cancel a subscription, and they're part of what powers those product recommendations you see everywhere. When you boil it all down, that's really the magic of a decision tree. It takes these huge, messy, complicated piles of data and turns them into a set of simple rules that a person can actually look at and understand. It finds the clarity in the complexity. And that kind of leaves us with this really cool, big-picture question. If we have this tool that can map out the path to almost any decision, from something small to something massive, what's the next big problem we should aim it at?